Hello everyone, my name is Abigail Marshall. Hope you enjoy this grand picture here, which is a none too obvious hint of what this presentation is all about. My project basically involved simulating the impact of acid rain on carbonate stone and on non-carbonate stone, and then also I studied a lot about the history of acid rain and studies that are similar to my experiment and its impacts on human health and ecosystems and organisms and those sorts of things. So since I'm presenting this in an online format, I've included more information on the background to acid rain and its impact on Earth than I possibly would have in a offline environment. So if you're not too interested in that and you just want to get a quick overview of what acid rain is and it's a summary of its impacts in like one slide and then skip ahead to the description of my experiment, I will be providing a like minute and second marker in my post on Blackboard and possibly in the description of this YouTube video if you want to skip ahead to that. So just as a general overview, acid rain is a truly global problem that has long-term negative and sometimes even destructive impacts on both terrestrial and aquatic ecosystems and organisms, food crops, stone structures, and soils. The term acid rain refers to atmospheric deposition of acidic constituents that impact the earth as rain, snow, particulates, gases, and vapor. And that was basically the definition given for it by one wide-ranging study that was conducted on this topic in 2016. Sometimes acid rain is used as a general term to refer to both dry and wet acidic deposition. Wet acidic deposition refers to acidic particles that are deposited on the earth in the form of rain, snow, gases, or sometimes vapor. And dry acidic deposition refers to acidic particles that are deposited in the form of like a dust substance. And the dry acidic particles will basically be absorbed into the soils and stick to man-made structures and vegetation. And when they are washed away by rain, that will basically contribute to acidic runoff that then will deposit into larger bodies of water. To my surprise, despite continuing to be an ongoing topic of study, acid rain was first identified as early as 1845, and it's been studied in some way since the mid-19th century. So during the Industrial Revolution time period, basically around the 1850s to 1870s in this case, an English chemist named Robert Angus Smith became the first to identify acid rain as an environmental pollutant, and he identified it at the time as the byproduct of emissions from industrial facilities, basically factories. And then from the 1960s onwards, European and North American scientists such as Stefan Odin in Sweden and Gene Likens in North America pioneered studies on where acid rain came from and the harmful effects it had on the environment. And these sorts of studies basically led to our modern understanding that acid rain is caused largely by regional emissions of sulfur dioxide and nitrogen oxides. And these are basically the acidic particles that comprise the majority of acid rain. So these studies caused the government, citizens, media, and policymakers in North America and Europe to take notice of acid rain as a serious environmental problem and to take steps to combat it, such as strictly regulating emissions of air pollutants. And these measures have been largely successful as emissions of acidic particles have been steadily declining in North America and Europe since the 1970s and 1980s. It's not that case everywhere in the world though. Like Southeast Asia and India, emissions of sulfur dioxide and nitrogen oxide particles continue to increase. So acid rain is still causing significant damage to ecosystems and organisms in other parts of the world. and it is still causing damage to ecosystems and organisms in North America and Europe as well. It's just the extent of the damage is less than it used to be. So in addition to leaching heavy metals from soils, acid rain also interacts with aluminum and mercury in soils and changes them into heavy metal compounds that are then absorbed by and can significantly harm plants, soil microorganisms, and aquatic ecosystems as well. And this in turn affects the entire food chain. And according to the Environmental Protection Agency, otherwise known as the EPA, the ecological effects of acid rain are most clearly seen in aquatic environments. Many aquatic organisms die or have their growth or reproduction inhibited, both directly and indirectly, by acid rain and the heavy metals that it leaches from soils, which I was discussing on the previous slide. Acid rain also decreases the amount of oxygen that's available in aquatic ecosystems, which is especially damaging to fishes. And this is perhaps why acid rain has led to a significant decrease in the population numbers of shellfish and some other fish species in coastal waters in the US over the years. And even though some species can tolerate or quickly adapt to the situation, the organisms they eat may not be able to do the same, which means that these species that can compensate will still often be endangered due to their food sources being killed off. For example, aquatic frogs can survive at a pH of 4.0, which is the average pH of acid rain, but the mayflies that are their primary food source cannot survive below a pH of 5.5. Acidic particles and heavy metals also bioaccumulate in individual organisms and undergo biomagnification as they go up the food chain. And just a quick review of those terms, that basically means that organisms higher up in the food chain will have higher concentrations of acidic particles and heavy metals, and individual organisms will absorb these particles and heavy metals at a faster rate than they excrete them, which leads to accumulation of them in their bodies. And interestingly enough, the EPA was saying that even ecosystems that are only exposed to acid rain once in a while will still or can still be significantly damaged by it. Acid rain can also negatively impact human health, particularly dry acidic deposition, because the acidic particles that make up the majority of acid rain, which are sulfur dioxide and nitrogen oxides, as previously mentioned, basically interact as gases in the atmosphere to form fine sulfate and nitrate particles that can be transported long distances by winds and inhaled deep into people's lungs. And this, of course, causes health issues in the lungs and heart, such as heart attacks, asthma, and bronchitis, or it increases the risk of those things. And it also irritates the skin and eyes, and inhalation of high concentrations of these sulfate and nitrate particles can also lead to cancer. In a more indirect manner, nitrogen oxides and acid rain also react with these things in the air called volatile organic compounds, which creates tropospheric or ground level ozone. Now, of course, while ozone in the stratosphere is beneficial because it helps protect life on Earth from ultraviolet radiation from the sun, ozone created at this tropospheric level is bad and can lead to all sorts of damage to ecosystems and health problems in humans, such as chest pain, coughing, throat irritation, airway inflammation. It can even damage lung tissue and worsen existing respiratory conditions. An important disclaimer, though, is that according to the EPA, walking in acid rain or even swimming in a lake affected by acid rain is no more dangerous to humans than walking in non-acidic rain or swimming in non-acidic lakes. So most of the negative impacts on human health from acid rain come from inhalation of those sulfate and nitrate particles rather than like acid rain hitting your skin or something like that. Acid rain significantly impacts stones by physically and chemically altering them, and this leads to a lot of damage to like stone monuments and buildings and statues and other stone structures like the Taj Mahal and the Statue of Liberty. This is why a lot of those old stone structures will have discoloration, or you'll see detailing being lost over time. Some sections of them will be completely lost because the acid rain has completely dissolved that part of the stone. The surfaces will become rough over time and those sorts of things. Stones that contain calcium carbonate or other carbonate compounds have consistently been shown to be the most susceptible to degradation by acid rain, and these sorts of stones include limestone, marble, and calcareous sandstone. Basically, the acid rain will dissolve the calcium carbonate or the other type of carbonate compound in these sorts of stones by turning it into a soluble hydrogen carbonate or like calcium bicarbonate. So basically it will dissolve that carbonate compound and it'll be washed away. So similar to old studies that attributed the ultimate or root cause of acid rain to acidic particles being emitted from human activities, a recent study by a team of researchers in India stated that currently the key acidic particles that contribute the most to acid rain originate from human activities such as combustion of burnable waste, fossil fuels, and thermal power plants and automobiles. So some measures that can be taken to reduce or combat acid rain are actually pretty similar to measures that can help climate change overall, such as reducing the use of fossil fuels and switching over more to green forms of energy, such as hydropower, wind power, solar energy, and geothermal energy. And also, this team of researchers in India suggested that reducing the use of cars could also help combat acid rain. Acid rain can also be neutralized by alkaline compounds in stones and soil, especially by the calcium carbonate and limestone. And as you'll see later, the results of my experiment definitely proved that to be true. In addition, however, slightly acidic soils and typical evergreen forests in the northeastern part of the US, Canada, and Europe can also neutralize acid rain by absorbing the ions from the nitrogen oxides and the sulfur dioxide in acid rain. The extent to which soils can neutralize acid rain depends on several other factors though, like the type of soil, whether the soil is frozen over or not, and how thick it is, and those sorts of things. So my study aimed to confirm the findings of previous studies that indicate that acid rain is typically neutralized by and also degrades limestone. And also my experiment aimed to compare and contrast the impact of acid rain on carbonate stones, which were represented by limestone in my study, and on non-carbonate stones, which were represented by granite in my study. I was particularly interested to see how granite would be impacted by acid rain because even though granite is traditionally assumed to be very resistant to weathering by acid rain, several studies by Japanese researchers have found that granite, as well as other tough rocks that are traditionally assumed to be impervious to acid rain weathering, are actually chemically altered by acid rain, which suggests that they are indeed susceptible to weathering by acid rain, even if it's at a slower rate than carbonate stones. So several other studies have also simulated the impact of acid rain on both carbonate and non-carbonate stones, and I've listed several of those in parentheses there. A carbonate stone in these studies was usually represented by limestone, and pretty much all of these studies used passive immersion as at least one of the methods by which the stones were exposed to acid rain. Passive immersion basically entails exposing the stones to a diluted acidic solution that is supposed to be the same pH as the average pH of acid rain. And basically the stones are just immersed in that acidic solution for a certain period of time. So the first blurb on this slide is pretty similar to what I was discussing on the previous slide. And basically how my experiment was conducted overall is that 4 pieces of granite stone and 4 pieces of limestone were exposed to 100 milliliters of diluted sulfuric acid solution over a period of 25 days, with each of the stones being in their own separate enclosed plastic containers. The sulfuric acid was previously diluted with water. I didn't do that, it just came pre-diluted, and this was so that it could have a pH of 4.0, which is the same as the average pH of acid rain in the environment. And then before I added any acidic solution to the plastic containers, each of the stones were weighed using a tare scale, and then those weights were recorded as their initial weights. So the two groups I divided the stones into was a group where I added the diluted sulfuric acid solution on the first day, and then those stones remained in that same acidic solution for the duration of the experiment. So that group I left alone, I didn't touch. And each group, by the way, had 2 pieces of granite stone and 2 pieces of limestone. And then the other group, I regularly changed out the sulfuric acid solution every Monday, Wednesday, and Friday of each week. And basically how I did that was I would just dump out the old sulfuric acid solution into a separate sulfuric acid waste container using a filter. And then I would just measure out 100 milliliters of fresh diluted sulfuric acid solution into those 4 bottles. Each group had 4 bottles. And then this was basically done to compare the impacts of like old acid rain on carbonate and non-carbonate stone, and the impact of like fresh acid rain on carbonate and non-carbonate stone. And of course the old acid rain was represented by the group where the acidic solution was not changed out ever for the duration of the experiment, and then the fresh acid rain was represented by the group that underwent regular exchanges of that diluted sulfuric acid solution. So on the last day of the experiment, which would be day 25, the pH of each of the solutions in the containers was measured using a hydrogen pH testing paper, and then those pHs were recorded and compared to the initial pH of that diluted sulfuric acid solution, which, as I previously mentioned, was 4.0. And then the acid from each of the individual plastic containers was dumped into the sulfuric acid waste container, and then each of the stones were rinsed with water for approximately 20 seconds to get off any remaining acid, and then they were left to dry for approximately 4 days and 7 hours. And then the stones were left to dry so that their final weight would be a dry weight, just like the initial weights, so that no acid or water would be accounting for any of that final weight value. And then in order to track what the initial and final weights of each stone were and which group each of the stones came from, each stone was left to dry in separate open Ziploc bags that were previously labeled with the same information that was on the plastic container that that particular stone came from. So that was like the initial weight of the stone, what type of stone it was, and which group it came from. And then after the stones finished drying, they were weighed again using the same tare scale, and then those weights were recorded as their final weights and then compared to the stone's initial weights. So this is just one picture of part of my setup. To the far right here is the sulfuric acid waste container, and then next to that on its left is one of the bottles of diluted sulfuric acid solution that I would add to the containers, or regularly add to at least half the containers. And then next to that acidic solution bottle is the granite, and then next to that granite is the big chunk of limestone that you see there that has the number 41 on it. And this is just a picture of the plastic containers that each of the stones were kept in. So on the top half, the long-term part of that green tape label indicates that those are the stones that did not undergo any exchanges of the sulfuric acid solution. And then on the bottom half, you see that the short-term part of that green tape label indicates that those stones underwent regular exchanges of that diluted sulfuric acid solution. So moving into my results now, at the top here, I point out this aberrant granite stone number 1 that was part of the group that remained in the same diluted sulfuric acid solution for the duration of the experiment, because the results for this particular stone deviated from the trends and the results that I got for all the other stones. One of the ways that it deviated was that it exhibited the highest percentage of weight loss compared to all the other stones over the duration of the experiment, as it lost approximately 0.6% of its weight, and then you'll be able to see that in figure 1 in a later slide. And I also noticed that it deviated from this trend here of stones that had lower initial weights exhibiting higher percentages of weight loss than stones that weighed more initially. So granite stone number 1 deviated from this trend and that it lost more weight than its counterpart in the group that underwent regular exchanges of acidic solution, even though this deviant granite stone weighed more than its counterpart. So that's just one example of how it deviated from a trend that I noticed in all the other stones. So one kind of interesting side trend that I noticed was that for both the limestones and the granite stones, the stones that underwent regular exchanges of the diluted sulfuric acid solution ended up being a significantly lighter color on the last day of the experiment than their counterparts that did not undergo any exchanges of the diluted sulfuric acid solution. So in this picture on the right is one of the limestones that underwent regular exchanges of the acidic solution, which, as you can see, is significantly lighter than its counterpart on the left that did not undergo any acidic solution exchanges. And so continuing with just one other picture of this trend, here in this picture on the right is one of the granite stones that underwent regular exchanges of the diluted sulfuric acid solution, and as you can see, this granite stone is significantly lighter than its counterpart on the left here, which did not undergo any acidic solution exchanges. So some other trends that I noted for the weight loss of the stones were that when the weight loss percentages of limestones and granite stones that had similar initial weights were compared, the limestones lost more weight than their counterpart granite stones, and this was the case for both groups. So the group that underwent regular acidic solution exchanges and the group that did not. And comparing the percentages of weight loss between stones of the same type, so both limestone and granite in both groups. With the exception of the aforementioned aberrant granite stone, the stones that underwent regular exchanges of acidic solution lost more weight than the stones that remained in the same solution for the duration of the experiment. So this is figure 1 for my experiment, and it is the initial weights, final weights, and percentages of weight loss for the stones that did not undergo any exchanges of the diluted sulfuric acid solution. Here in the third row, you can see the infamous aberrant granite number 1, which exhibited the highest percentage of weight loss, even though it had the second highest initial weight. And this deviated from the trend of both limestones and granite stones losing less weight if they had higher initial weights. And regarding the trend of limestones of similar weights losing more weight than their granite stone counterparts, we see here in the second row that even though limestone number 2 was only 1.14 more grams than its counterpart in the last row, granite number 2, it lost approximately 0.08% more weight than its granite counterpart. So here is figure 2 for my experiment, and it is the initial weights, final weights, and percentages of weight loss for these stones that did undergo regular exchanges of the diluted sulfuric acid solution. And I may have forgotten to mention in the methods, but the initial and final weights were recorded in grams, as one would expect. Regarding the trend of limestones losing more weight than granite stones of similar initial weights, you can see this here, and that even though granite number 1 in the third row was only about 0.6 more grams than limestone number 1 in the first row here, limestone number 1 lost approximately 0.15% more weight than granite number 1 in the third row. And regarding the trend of, at least among stones of the same type, those that had higher initial weights lost less weight than those that had lower initial weights. So for example, in row 2 here, you can see that limestone number 2 was about 2.62 grams more than limestone number 1 in the first row, and it lost about 0.04% less than limestone number 1. So looking at trends in the pH results, for both groups, the solutions that were exposed to limestone had higher pH values when they were measured on the last day than those that were exposed to the granite. And the limestones that remained in the same diluted sulfuric acid solution for the entire experiment actually turned the solutions into alkaline ones, because the limestone increased the pH of these solutions from 4.0 to 8.0, which you'll be able to see in figure 3 on a later slide. And then the granite stones that remained in the same diluted sulfuric acid solution for the entire experiment also increased the pH of those solutions, but significantly less than the solutions that were exposed to limestone. The granite increased the pH of these solutions to 5.0. So looking at pH trends and the results for the group of stones that underwent regular exchanges of the diluted sulfuric acid solution, the limestones in this group also increased the pH of the acidic solutions, but not as much as the limestones that remained in the same acidic solutions for the entire experiment. And then neither of the granite stones in this group that underwent regular exchanges of the acidic solution changed the pH of the original diluted sulfuric acid solution. So this is figure 3 for my experiment. It is the pH values that were measured on the last day for the stones that remained in the same acidic solution for the entire experiment. So as you can see, both the limestones in this group double the pH of the diluted sulfuric acid solution from 4.0 to 8.0, and both the granite stones in this group increase the pH of the acidic solution as well, although not as much. They just increased it from 4.0 to 5.0. And then in the last figure here, you can see the final pH values of the diluted sulfuric acid solution for the group of stones that underwent regular exchanges of that solution. So as you can see, neither of the granite stones changed the pH, but the limestones did. One of the limestones increased the pH to 6.0, and then the other limestone increased the pH to 6.5. So the results of this study confirmed previous studies and reports that indicate that acid rain has a sort of mutual relationship really with carbonate stones, because while it does significantly weather them, causing them to lose weight and ions and that sort of thing, it is also significantly impacted by them as well. And we especially saw that in this experiment's results with the limestone that remained in the same diluted sulfuric acid solution for the duration of the experiment. It completely transformed that solution from an acidic one to an alkaline one, as it doubled its pH from 4.0 to 8.0. And the fact that limestones lost more weight than granite stones that had similar initial weights in both groups supports previous studies stating that the calcium carbonate in limestone is especially susceptible to weathering by acid rain. So that is sort of an expected result. And the fact that the granite stones that remained in the same diluted sulfuric acid solution for the duration of the experiment did change the pH of the solution supports previous studies done by Japanese researchers that state that granite and other similarly resilient stones are actually weathered by acid rain, albeit at a significantly slower rate. And this would also explain why the granite stones that underwent regular exchanges of the acidic solution did not change the pH of those solutions, because when the pH was measured on the final day with those solutions, those granite stones had only been in the acidic solution for about 3 days. So they were not probably exposed to the acidic solution long enough to be altered by it, or for them to alter the acidic solution. So the fact that all stones in the experiment underwent weight loss is consistent with similar studies that found that both carbonate and non-carbonate stones, including even artificial stones, experience weight loss after long-term exposure to acid rain. And the fact that, with one exception, which would be the aberrant granite stone number 1, the fact that the stones that had lower initial weights exhibited more weight loss is likely an indicator that smaller stones experience the impact of weathering from acid rain at a faster rate. So this could be due to the fact that smaller stones have lesser amounts of the compounds and elements that help shield them from weathering by acid rain compared to their larger counterparts. So the fact that stones of the same type that underwent regular acidic solution exchanges lost more weight is likely due to the fact that the fresh diluted sulfuric acid was more potent and that would mean that the stones that were regularly exposed to that fresh acid experienced its weathering impacts at a faster rate. And I think a likely reason for the aberrations exhibited by granite number 1 and the group that did not undergo any acidic solution exchanges is that it may have contained more of the minerals and compounds in granite that make it more susceptible to weathering by acid rain than traditionally assumed. Previous researchers have stated that chemical composition is an important factor in how stones are weathered by acid rain, and a group of Japanese researchers that studied the impact of acid rain on gabbro, which is fairly similar to granite in terms of its resistance to weathering, found that certain chemicals in the gabbro were much more susceptible to being altered or dissolved by acid rain than other chemicals. So it could be the case that this particular granite stone had more of those chemicals that are, or higher concentrations of those chemicals that are more susceptible to weathering. So in conclusion, the fact that limestone is so effective at neutralizing and alkalizing acid rain has important implications for how acid rain's impacts can be mitigated, as it indicates a potential natural solution. And this is especially important because several countries have been either late in adopting other sorts of practices to reduce the emissions of acidic particles, or they have yet to adopt such practices at all, and emissions of acidic particles are continuing to increase. So really capitalizing on the role of these alkaline soils and carbonate stones in particular in neutralizing or even alkalizing acid rain would likely be faster and perhaps easier solutions to implement starting in the more immediate term to help combat this really insidious ecological problem. That's not to say that taking other measures such as switching to greener forms of energy and imposing more regulations on air pollution are important. It's just that I think these sorts of studies and my experiment confirm that these carbonate stones and these soils that can neutralize acid rain play an important role alongside those more political decisions and combating this problem in the more immediate term. And so ultimately today, even though acid rain was first identified as an environmental pollutant as early as 1845, it still represents an unintended hemispheric scale ecosystem perturbation experiment that warrants ongoing study. That was according to this wide-ranging study on acid rain from 2016. So today, scientists are continuing to study and observe how ecosystems in various regions are recovering from acid rain, and as well as how this recovery can be aided. And also just they are investigating the long-term effects of acid rain on wildlife and vegetation, and also comparing that with the results of reduced levels of acidic deposition on wildlife, vegetation, and other ecosystems. So hopefully this presentation gave you guys a good overview of this issue and proved that while a lot of people think acid rain is not that important of an ecological issue anymore, or it's an old issue, it actually is still a very relevant ongoing topic of study that has honestly been one of the topics I've seen that has been studied for the longest period of time, well over a century by now. And these are my references here. Another page of references. Another page of references. Another page of references. I think this is the last page of them.